So hello, I'm Oliver Gao. I'm the director of Cornell Systems Engineering Program. I have been running these system conversations with our great speakers that we brought to our program through our Israel System Seminar Series. Today we are very delighted and honored to have Professor Biao Huang. And Biao is a professor and also the NSERC Senior Industrial Research Chair in Control Oil Sands Processes. And also he is the AITF Industry Chair in Process Control with the Department of Chemical and Materials Engineering from the University of Alberta. And I also wanted to point it out that actually Biao, he serves as the editor-in-chief of a very important world-renowned journal, which is that Process?
Yeah, it's the IFAC Journal of Control Engineering Practice.
I was reading the bio of Dr. Huang. I was so impressed with so many achievements and accomplishments you've done. And I think, of course, you had the international background, and you did your PhD study there at Alberta, and then, you basically built your career, and not only a traditional career, as a researcher, as a university researcher. I saw that you have had so much successful collaboration with industry. So I think, and of course, a lot of things are very systems oriented. I think as a program from system point of view, we are very curious to learn more about your own development and your career and also your research.
Mm-hmm. Mm-hmm. Okay, so you introduced a very well introduction, and our program at the University of Alberta, we call it as computer process control. Mm-hmm. And this was built in 1970s, mm-hmm. and with some senior professors. They all retired now, but they started the program. And when they started the program, the focus was on control. Control is very specific. So we call automation, sometimes call automation or control engineering, control theory. And when we went to this new era of industry development, and then we found that the control itself may not be scope, maybe too narrow in solving the general problem of the industry. Of course, we have a lot of theoretical development, very nice theory, mathematics, and very advanced. But to connect to engineering system or an industry, we not only need to know the control theory, but also need to know the process.
The domain knowledge.
Domain knowledge, yes. Mm-hmm. So the chemical or electrical or civil or mechanical, robotics. So you need to have this domain knowledge. And to communicate with industry engineers, and if you just talking about control theory or control itself, they may not understand. Mm-hmm. But they first need to ask you, do you know the process? Do you know what you are controlling about? So our program evolved from the need of industry. Mm-hmm. Alberta is very heavy industry. Chemical processes, oil, chemical, petrochemical, so very well developed. So we have a lot of demand, the need from industry. Mm-hmm. So from this driven force to make our program evolve, to a scope getting bigger. So we consider system engineering. So since end of 1990, I think around 1990 to 2000, we start talking about system engineering. And so our program also expanded, and we have quite a few faculty members in even chemical engineering. So in chemical engineering, we have 4 or 5 or 6 faculty members working in the systems and optimization, control, and monitoring, statistics, and so on. We also electrical engineering colleagues, and they also very close related with our program, and mechanical as well. So we start a lot of collaboration with industries. And for myself, and I started collaborating with, which is the major oil company And when I just started my career, which was the year of 1997, and has engineers start talking with me and talking about solving some monitoring and data analysis problem. And at that time, I just graduated from a university, from PhD program. I could work for about half a year in industry, but the industry knowledge kind of limited. But the demand from industry is there, right? So that forced me to expand my thought from this control theory or control engineering to include the process, the oil process. So let's start my whole program. So that we collaborate with for quite a few years. Of course, with support of our NSERC, which is the called Natural Science Research Council Canada, just like your NSF in US. And they support us, and of course, and jointly support with NSERC. And we have a program called CRD, which stands for Collaborative Research and Development Program.
I see.
And that is, I think it's a very good program to involve industry. So we start collaborating. So each CRD lasts for each project or CRD program lasts for 3 to 4 years. So we start doing CRD. The first CRD is small one. We try it, and found successful and solve some practical problem, basic system problem. Not just the deriving equations. You actually get the solution. We call deliverable. So helping them to solve problem. So we start CRD 1, CRD 2, CRD 3, CRD 4. So when we look at this funding level, it's increasing, like the stairs increasing, right? Significantly increasing. And of course, our NSERC also increased the funding. When we went to CRD 4, and industries in Alberta and realized this is good one, and we need to expand it. So we start including another industry, important oil company. So once we have more industry participating in the program, and we find the CRD itself, CRD not enough. So we expand to IRC, which called Industrial Research Chair program. It's also the flagship program in NSERC.
Is that an endowment?
It's not endowment.
Okay.
The program works in this way. So there are some very strict requirements on who can be the chair. And so, but another important criterion is, in addition to academic achievement, another important criterion is industry, the trust. So industry has to put a lot of fundings, and NSERC also put to match additional fundings, and through this rigorous evaluation, like we have called site visiting committee, number of committee members from the United States. Anyway, so we evaluate this, and then they look at the candidate, look at the program to see. Because the chair program look at the whole area. Like I'm the chair, industry chair, research chair in control oil sands process. So oil sands is very important industry in Canada.
That's true.
And so we need a good control system and engineering. So I was candidate and applied to NSERC and get peer reviewed, and we site visit, and they felt happy, and so they approved program. So 5 years for each term. So that is major jump in the research, meaning that the profile visibility will be much bigger than other program, and so industry start more companies start looking or finding our program attractive, and they find the solution useful. Anyway, so once we finish the 5-year term, and that time with the oil price dropped, which is a couple of years ago, and tough time to do any renewal, but interesting, very interesting. Other programs get the funding cut because the industry, oil, the price dropped a lot, from $100 to $28. So, but our program not only didn't drop, increase actually.
So maybe you can find something to help them deal with that situation.
Yeah, because system engineering very important in a sense. When in a downturn, when the industry in downturn, and you do need to, because in downturn time, and you do need to reduce the cost.
The lean process.
Yeah, reduce the cost, and so that is control or engineering, system engineering play role, optimization, control, and it will help to reduce the cost, right? Production cost, and that's very important for industry to survive when the price of oil drops so much, and so in downturn they found the control engineering or system engineering actually in even higher demand, and plus we did demonstrate to them we were able to help them to improve the productivity, efficiency. And so they like it, and they feel this is important. So we got so in the first term, we have two major oil companies. They were our partners. When we go to the second term, we got 5. So we expand by by 3. So basically, more. It's really says in the downturn, get more partners to get interested.
Because they need help.
They need help. They need it. Anyway, so I say system engineering is very important because you are solving. Essentially, you are communicating in the same language as they want. Right. So how to reduce cost by automation, and how to make a reliable operation, and these are all they want to know.
I'm so impressed that your program has had such a connection with the industry. So. And I think one key thing for system engineering, the first step is we need to understand like the requirement, the need of your client or of the stakeholder that our research is serving for. And I think so like your research I think really constitutes a very nice systems life cycle. Your research is actually initiated from the research problems or real world problems.
Yes, yeah.
Those companies they have. And then by helping them, and of course in the end, to solve those problems, that actually some problem will be translated into research problems, and then you move on. So this is really, of course,
cycle,
I think it's a really full cycle. Of course, in the end, and your research result will be applied to that. And I think in a lot of, I don't know how it is in other Canadian universities, but in a lot of, in the traditional universities, research didn't seem to be done this way.
Yeah, a lot of research. I think research different way, and a lot of research coming from the top down. So you have theory, and you get a theorem, and you want to verify the theorem and find some problem to solve.
That's right.
But some other research come from bottom up. So you have problem there, and there's no existing the practical problem. You could not find the solution to fit. Right away, no way, because the solution most solutions have a lot of assumptions, but practical one you cannot assume it is there. Right?
That's right.
Yeah, so not only to know the problem, but also to know the system, the process.
Yes, exactly true. Kind of, the traditional way a lot of people are building hammers without knowing where the nail is.
Exactly.
However, like you start with the nail and build the appropriate hammer and move on. So I think this is really, very important. And also, I think this kind of research, one, it has longevity because you have the source of problem, and two, and it really generates the impact that when you look back, at your career and you feel, you are not only having top journal papers published, you really had very significant impact to the society, right? I think that that's beautiful. So I think you are talking about this. Industrial Research Chair in control of oil sand processes. So, and you mentioned the importance, I think you illustrated the importance of system engineering for this kind of industry, especially when the industry was in the downturn, right? So, and now from a research point of view, what are the major research challenges or the research needs from the industry that your group has been serving?
Yeah, I can give some, I think it's best to give some examples. For control engineering, for example, the control theory is quite matured, right? And a lot of advanced control system design and algorithms. Now, one key thing people didn't pay much attention. The control has very important component, which is called sensors. So without sensors, you cannot talk control. There's no way. You don't see, you don't smell, you don't feel, you don't touch, you don't feel, and you cannot control it. So when we do the control development and control theory, we assume this measurement the variables. We never worry about can we measure it, can we know it, but we just assume they are there, right? But once you go to a real industry, like oil sands industry, the sensors are not there, or they are there but not very reliable, and because the measurement of the bitumen or the oil sands is not very reliable sensor you can find. So you don't have sensor or don't have very reliable sensors. And no matter how good control you have, it cannot operate, right? It cannot control it.
Yeah.
But now the sensor itself and is hardware. Normally hardware. Your hardware is not reliable. How are we going to solve a problem? How are we going to are we going to build another hardware? Which I don't think is going to work because hardware built by specialized company. It doesn't work well, and we cannot make it happen. Now it come out, can we do the inferential sensor? So we have some sensors which are very reliable, such as some pressure measurement, the liquid pressure, the air pressure, or gas pressure, or we have liquid levels, we have temperatures. They are relatively easy to measure and they're also very quick. The concentrations are very hard to measure the concentration of the component of particular substance, and they are very hard to measure the concentration, the component. So there's no good instrument to measure the component or concentrations. The question: can we use this easy to measured variables to infer those hard to measure variables?
That's a very smart one.
Yeah, then you need mathematics, right? So the question is, to do this, you certainly have a few different ways to do it. One way is build a first principle model, build a physics model, a mechanistic model, and build a model and derive equation. Now equation become useful, right? And we learn equations: heat balance, energy balance, mass balance, and reaction, and then that becomes useful. Build a model, and then the model built from first principle certainly need a lot of assumptions. So again, you have gap, or at least not going to be used. Not traditional modeling approach will not work. But you still need the model. Now the question: how to intelligently use this model to serve for our inferencing purpose? So that you need a lot of what we call corrections, compensations, and filtering, the common filtering, and sensor fusion.
Yeah, whatever methods you can use.
Exactly, and so when you do this, and you have to look at the reliability, the data reliability. There are sensors sometimes fail, and sometimes we have outliers. How we deal with outliers? How to make this equation robust? Right? So these are the challenge you have to solve. So robust estimation, robust regression, and filtering become important topic. So from there you get real problem, and then you lift up to get some nice theory around it, right? And so that theory is beautiful because coming from practical problem.
Yeah.
Alternatively, you cannot find any model, right? So in this case, we use the data analytics, the database, and now it become very popular topic. They call artificial intelligence or data analytics, big data, and it become popular over the last few years. But in fact, we worked on this problem a long time ago, right? And when you don't have good first principle model, and you have to use data, and the data high dimensional, you have to find which variables are important. Right? So 100,000 variables. You use all of them, and of course, you can use all of them. You can compress them and get a few features. But the question that use all variables, compress them, but all variables are still there, right? You get the core features. Any variable fail, it fail.
Mm-hmm.
So the question would, you will have good technique to compress the data, but if you blindly use them, not going to be useful in practice.
That's true.
1,000 variables, I use principal component analysis, I get 3, right?
Mm-hmm.
Very good, compress, and very simple. But question, 1,000 of them all used. One of them fail. Your compressed variable fail. So we come out how to select variable, how to causality analysis to make sure this variable selected, they are indeed the source and not cause. Right? So the causal analysis also become important.
Yeah, that's true. I think kind of, especially you mentioned that several years ago, all of a sudden this kind of data analytics became a major trend, either in academics or in industry. Of course, I think this is mostly industry driven, right? Because there is industry need, and also because of the advancement, all these sensing technologies that enabled this huge amount of data. Of course, I think now, you have been the person who before. You were using this kind of, you were developing this inferential methods due to the lacking, right, of data. And now, like you are working on the other end, with so much data. So you've been working on both ends. So where do you see, of course, the traditional mechanistic models versus kind of data-driven. So where do you see these two branches heading, and what would be the future? Of course, now so many universities programs are talking about data science.
Yes, yeah.
Right. Of course, some universities talk about data science just for the, for the sake of hype. But but for you as an expert, right? So so my question would be, the traditional model-based, right, and research, even inferential research, and versus now the data-driven,
yes, yeah.
And then towards the future, of course, with these sensors becoming more pervasive, the data privacy issues. So what do you see as an opportunity and a challenge for all these data analytics and versus the traditional modeling approach?
Yeah, I think the traditional modeling approach we all understand and we all know, and because anybody learn it, engineering we all learn this traditional approach. Now the data analytics is very successful in many fields, and no doubt, right? Like playing the chess and internet, serve internet, the statistics, the selling, and the .com, and they use this data analytics to determine your pattern of the buying and
the market research,
marketing.
Learn about the consumers.
Exactly, and the bank also use the data analytics to protect your credit card, for example. These are certainly very useful, very successful. Now for engineering problem, engineering issue, I think it's become more complicated in the sense of the pure data analytics, and without knowing the process, the systems, and just blindly use data. And from my own experience,
make sure our time.
My own experience tell me that for engineering solution, very often pure data solution may fail. And there are many reasons. And the process itself can change over time. The wearing, tearing, and that's all that, they change over time. And also, process is not like something like playing chess. Playing chess is repeatable, basically. It's kind of deterministic, although its combination is huge, but still deterministic. Meaning that if you know the way, the rule, and you can program it.
That's right. There are algorithms.
Algorithms, yeah.
Yes.
Of course, it's very big, and once you have enough computation power, and you are able to solve. Of course, you don't have computation power, you can still find the best way to optimize, solve it. But engineering problem is like some human being is changing. Right? It's not something which repeatable. It's not always repeatable.
That's right.
Yeah, it's evolve over time. Evolve over time. So if you use data analytics and you say, okay, I do the data analytics, a huge amount of data, and to build a model, And so build a data-driven model, you need a lot of data, no doubt. But question or engineering system or process system will long collect a lot of data over a year, 2 years. The model no longer same. Right? It's changing. The heat change, the falling of this, the model change. So it's a dilemma. So you need a lot of data to build a model. I can give you a lot of data, but unfortunately, the model is not same. And the model will change over time, or change the time over time. So I have a lot of examples, and for the process systems, for any problem, if we are able to solve using the process knowledge together with the data, I would recommend do that way. To know the process, try your best to get the process, to get the knowledge of process, then complemented by the data. This is best solution. Of course, in some case, you don't have process information. The only way to do is you just need the data. Even in that situation, you still need to want to find, I'm not able to build the first principle models. Can I find some relevant variables? Okay, which variables are relevant to build a model? So just don't use all data, blindly use data to build a model. You still want to sort it out and find relevant information. But I guess my point is, for engineering problem, you want to use as much knowledge as possible first. Then data come to help. Right? So that's my own experience, and I found that a lot of solutions we come from this way. And for example, in oil industry, we have refinery, upgrader, we have extraction. We call upstream, downstream. Upstream process are very complicated. There are not many good sensors, for example. Data not very reliable. And downstream process, refinery, they have very nice sensors, very mature. Yeah. So refinery refinery process is reaction. To build a first principle model are relatively difficult to build. But fortunately, data are very good.
That's true.
So in that case, and data analytics will help a lot. Of course, still need to have some information about which variables are important. For upstream process, and rely on the data analytics, not going to work well. So you need to build the first principle model. Upstream, fortunately, use mass balance. They can build a model. Energy balance. They normally don't have reaction. So you have nature also sometimes interesting. So they help us for this particular process. We can build data. For that one, can build a first principle model. Of course, all we correct by data. So I think combination of both are good. So you cannot separate them, particularly for engineering. And for computer science, maybe different story. But for our perspective, we have to synthesize both different approaches to come up with best solution.
Yeah, I think that's actually the beauty of working closely with industry, because you want to solve the problem. That's the key. It's not kind of because my domain, my research interest is in data science. I would just data analysis. I would just put. Instead, you are trying to use all these different ways to solve the problem. I think given that I can see the whole benefit of you working closely with industry. So now, if you look back, kind of, if you would share with people, kind of what. If you can summarize, what would be some critical components to successfully collaborate with industry? Because I feel from our conversation, I feel that benefited your research and your research group, and even your university tremendously by having a close tie. And honestly, Cornell is not doing a very good job in terms of having very close collaboration with industry.
You're humble.
Yeah. So this is actually something, we may kind of learn something from you. So what would be your tips?
Cornell has a lot of things for us to learn. You are top university. Certainly, we have a lot of things to learn from you. But you talk about my own experience and 2 cents. And I think to work with industry, first you need to speak a language. Essentially, you need to communicate with the language. So to say that way, it really says you need to really understand the people, engineers, what they are doing, and you need to spend time to understand the process, essentially, systems. This is why I call system engineering. So not just system means a number of components.
That's right.
And put together a system. So you need to know all component, not just knowing the theory, some equations. You need to know the other side, each component, even sensors, the process, actuators, and how people operate the process, how operator operate the process, how engineer tune the controller. This kind of knowledge will be useful and helpful. So I think, put a simple way, to collaborate with industry, need to talk the same language to start. And once you have that, and you can follow up by providing advanced solution, because we are good in developing theory, right? So you get problem in your hand, you can develop theory. Then theory will translate into solvable solution, into applicable solution. They will happy about it. So then, okay, great, and then we have problem, and they got or we have a collaborator, and he always, a manager, he always says, if you have a problem, go to talk to Biao. He knows mathematics.
Okay, that's
mathematics.
The word.
They say mathematics is magic. So
Yes.
some problems able to write some equations. Somehow you solve problem. I think that's beautiful for us, right? And we get problem and mathematics. Eventually come back to them and look at this mathematics.
That's a very good word. Yeah, yeah. I think that's true. It's kind of, yes, you can translate real world systems problem into necessary mathematical problem. Sometimes the problem doesn't have to be translated into math, right? But sometimes I think it has to be translated into theoretical problem so that we can have the insight.
Right. Yeah. Although the final solution, implemented solution, may not be as complicated as the high level one, but high level one gives you a benchmark. So ideal situation, this is the best one can do. But translate back to the system implementation, you need to simplify them, to which you back down and to lose some performance, but make the implementable, which is important for industry. Deliverable, another one is deliverable. So I forgot to mention, deliverable, very important, right? And you cannot just get a publication thesis. Of course, it's good, important, but for industry, and if they don't see the benefit over a couple of years, 3 years, they were not going to continue. And our program start from 1997 until now is over 21 years, and sustained 21 years. So the is we always try to deliver. So we have a lot of publication, but meanwhile publication is one aspect. But I always tell my team member, so if you have good publication, that's good, but make sure deliver the outcome to the industry.
So the partners get what they want.
They need, otherwise there's no point for them to sponsor.
That's true.
Yeah, so that's very important, deliverable.
This is not only important for us as researchers, I think even as an individual, right? So how you deliver value, added value to whoever that come to you, right? So in that sense, in our program, we have a program of Master of Engineering, Systems Engineering, and also 2 years ago we started our PhD in systems. We dropped the word engineering. It's not PhD, just PhD in systems, because as you realize,
mathematics,
it's not only engineering. Human behavior, organizational behavior, the decision. So, from your success, what would you say to these future system engineers? What would be the key expertise or training that you see as important?
Yeah, I may be biased, but what I'm thinking that for systems, there are few components. One important thing I think is with the mathematics, particularly statistics, probability, will be very important component. It is the fundamental, and what I specifically emphasize on probability and statistics. System dealing with the practical problem. When you have practical problem, you always have uncertainty. Okay, the chance. So that probability statistics will help you. And the domain knowledge. Domain knowledge meaning that the system still need some specific system, electrical, chemical, or mechanical, still domain knowledge you still need. And system originally coming from control, so some control fundamental will still be necessary to have control. In the past, when we say control, we talk about system. But now system become really the world system even bigger than the control itself. But control system itself is still important, necessary to understand and how it works. It has system concept there. So I think that mathematics and domain knowledge and control knowledge will be necessary for the system.
That's beautiful. That's why I think we were teaching the students, we were emphasizing for the system students, we would like to help them establish a knowledge structure like in a T shape. You know, you have the vertical bar represent, that's what, you know, we don't have undergraduate programming system. We want to have graduate program.
I see.
Because, you know, student came to our program with undergraduate training in specifically certain domain, right? And of course they will, when they come to that program, they will keep being trained in this domain, but in the meantime, we also add a horizontal bar to expand their knowledge base so
That's
that
good.
they can work cross-disciplinary.
Right, yeah, that's good T shape.
That's a
Good analogy.
Yes.
Yeah.
Yeah.
Thank you.
Thank you
so
very
much.
much.